Welcome back to Quarks and Quarter Notes. Today we are joined by Karamvir Gill. Karamvir is an engineering physics undergraduate who is working on research with lunar dust. Today we'll be talking about his work along with several other physics-related topics. If you enjoy this discussion and would like to hear more like it, be sure to subscribe and leave us some feedback. Karamvir, could you introduce yourself and give us a brief bio about you?
I'm currently studying engineering physics at McMaster University, located about an hour away from Toronto. I'm in my undergraduate studies. I'm going into my third year. This summer, I actually happened to get in touch with one of the professors at Baylor University, Dr. Matthews, and her research is related to anything with dusty plasma, so any type of plasma-related research in cosmology and whatnot. And they had a project which I was super kind of interested about, which is learning about how we can model lunar dust lofting on the moon. And if you're not familiar to what lunar dust lofting is, basically on the moon, the gravity is different. So the way that the dust acts is different to how it acts on Earth, and it's charged by solar winds, so like from the sun. And what we're doing is we're looking at modeling that and seeing how like the lofting effect works, and seeing how if we can modify the conditions and compare it to experimental results. I'm also affiliated with school's rocketry teams, and I'm also helping out in the research and development of University of Toronto's Hyperloop team.
So I know what engineering is and I know what physics is. What exactly is engineering physics?
Good question. So engineering physics is a type of stream where you don't exactly, it's not too known. So it's basically looking at the wide variety of engineering disciplines, and we try to apply like a first principles approach, like really think about the physics behind it and really understand why it works, not just how it works, right? And if we can break it down and understand it to like a much physical representation, so more, math, simulations, physics, whatnot, and then we kind of get a better grips of it and see how we can apply it to, solve problems in the world.
So it's not quite like applied physics, right?
It's not like applied physics, no. It's still an engineering degree, like on paper, but it is called like a Bachelor of Engineering and then Bachelor of Engineering Physics, right? And we have a lot of like opportunities to take different classes from different streams, and that includes like math and physics department classes. So I've had the opportunity to take classes that like a conventional like engineer wouldn't take.
I think it'd be cool to talk a little bit more about your research. So you're saying you're working with lunar dust? Could you expand
Yeah.
upon that?
What happens is, like I said, is that the solar radiation, the solar winds, they're able to charge the particles on the moon, like the dust particles, right? And because they're being charged and the gravity on the moon is like, I think 5 times less, and that's why, you see videos of astronauts and they're able to like get some like hang time when they walk and whatnot. And you see astronauts' spacesuits after they come to the moon or found the moon, they're up to their knees, they get covered in dust, right? So it is something that like if there's any type of electric field, it can be excited and it could be lofted, right? And the whole thing is like, imagine you had dirt on Earth, right? And it can be raised by the sun and whatnot, and we need to predict how it's gonna be raised, like by the sun or whatnot, because that could interfere with a lot of applications that we're gonna have on the moon, right? So, and what we do is we're looking at the simulations and modeling them. So there's a lofting condition. The lofting condition, from my understanding and what I'm doing right now, is that you have the electric forces. So your electric forces from the sun, and they're charging the particles. And let's say you have an aggregate of particles, meaning like a large collection of particles. And from what it's charging, it has to be greater, like on each particle, the force has to be greater than the gravitational forces and the contact forces, like the adhesion forces. Like if you think about Newton's third law, for every action, there's a opposite and equal reaction, right? So these forces, just like if you have two people standing next to each other, touching each other, they have contact forces, they have adhesion forces, right? So it has to be able to break that with the electric charging from the sun. and we're looking at modeling that. It's if you want to establish a lunar base, we need to know how the atmosphere is, and one of the components is like how lunar dust reacts to electric field components and solar charging.
Simulating dust to me seems kind of hard. There's an awful lot of
It is.
particles in dust, right?
So it is because right now we're looking at spherical grain dust particles, and on the moon they're not spherical.
Right.
The jagged edges, and that's where it could be harmful if they're lofted, and it is definitely something hard. But we're looking at the like a very simple approach, and I say simple, but even to me it's not simple because I'm having troubles with it every day trying to figure out the code for it. But there's definitely more research that has to be done and simulating non-spherical dust grains and jagged edge dust grains. But you got to start off with the basics somehow. So I
Right.
guess that's what they're
Start
doing.
with what we know.
Yeah.
That's really interesting. So moon dust is basically a big hazard for equipment, and
Exactly. Yeah.
understanding it better will help us build equipment that is more resistant to the problems it causes.
More resistant, more able to account for lofting effects, like I said. I would really suggest like looking at any type of Apollo missions, and you could literally see
There's
like
so
the
much dust. Actually,
everywhere, right?
I've heard lunar. What are they called? The people who deny we've been on the moon. I don't remember their
Oh, those
official
people?
title. I've heard them complain that the dust doesn't behave like it should in a zero-G environment and stuff. But I imagine all those differences can more or less be explained by what you were talking about with the solar rays and the jagged edges.
Mhm.
And
No atmosphere. There's a lot going
No
on there.
atmosphere, yeah. It's something cool to look up, do research about because I get to look at the moon almost every night. I'm like, oh, cool. Like, I'm
Yeah.
kind of working on something
I'm
that's
studying
somewhat
that.
related,
Yeah.
but
So, how much do you think we know about the lunar dust and how it interacts? Do you think we're accounting for all the forces there, and it's just like a complexity issue just because dust is hard to simulate, or is there other forces that we're not or could not be taken account of?
there's a much more complicated problem from the simple problem I'm working on, and we want to go to the complicated problem, where is that the electric forces could break off into two different types of electric forces. So, electric forces meaning that one would be your attraction Coulomb force that you learn in, I think, high school physics. And then another branch of electric forces that we have to, like, we're looking into getting into, but I don't know if we'll be able to this summer, is the electric sheath shield force. So, if you have an aggregate of lunar dust particles, meaning like a collection of them on the moon, and they all contribute some electric field as well above the ground. So that electric field also has something to do with the lofting effect. And once the Coulomb forces, like you said, like they get weaker at a distance. So once a particle has already been lofted from the surface, right? It's the Coulomb forces are not too much, affecting it. And the electric force they do is from the sheath, meaning like the ground layer creates electric field, and that's what affects the dust while it's lofted. So definitely, we know like kind of more or less how it works. It's just modeling it and simulating it and using like the experimental knowledge that we do know. It's something that's gonna be ongoing. I don't like it's not
Right.
like you can solve this problem. It's just you just want to learn more about it, I think, and that's what
Exactly.
we're all trying to do there. Another cool thing is that with Baylor, why I kind of did this first and now another topic. I don't think I mentioned this before, but they have a UCOS group. So this is an early universe and strings group. So they're affiliated with string theory, and being an undergraduate, it's something that it's I'm not supposed to know, or like not really supposed to understand, but I think every physics undergraduate, Tyler, you could probably relate to this as well, is that you hear something like string theory, you hear something that like 11, 12 dimensions, and like what is this phenomenon, and what are they talking about? Yeah, string theory is something it's hard to wrap your mind around, but you can definitely explain it, but the math is very, very complex.
Right. So I've heard string theory explained and I've attempted to explain it, but when I look at the
Mhm.
math, I really don't know
Yeah.
what I'm looking at. It makes no sense.
it is bizarre.
I can totally relate there. Theories like that, they kind of all emerge from like the black hole information paradox, and Hawking's work on that. So if you're not familiar, I can talk about the black hole paradox and black holes if you guys want. We could
I'll leave
talk
that
about
to
that.
Tyler.
It interests me. I mean, I know all about it, but I'm down to talk about it.
So, actually, Tyler, do you want to give me your description of what you know about black holes, and then I can
And
kind
the
of
black hole paradox.
yeah, and then I can kind of
Well,
talk about that
so
and
how I
see what.
understand it, how we understood black holes when Stephen Hawking was working on them is that whenever something falls into the black hole, it's essentially it's disconnected from the rest of us once it
Hmm.
gets past that event horizon. And then Stephen Hawking, he did work showing that black holes actually evaporate and they have a temperature. So if you
Hmm.
wait long
Yeah.
enough for a black hole, it'll get smaller and smaller and smaller and just eventually leave. And the
Yeah.
information paradox that Stephen Hawking showed is that we can know of all the things that went into the black hole, but whenever the black hole radiates away, what happened to all that information? And Stephen Hawking kind
Hmm.
of pointed out that he wasn't sure exactly what was going on because that's one of the that is like the rule of physics is that
Yeah.
information is conserved.
Like it defies all of physics. So what black holes originally there was a guy named Schwarzschild
Schwarzschild.
or Schwarzschild, yeah, and we learned about him in general relativity. So I think he was fighting World War I, and he was in the trenches, or like, because I'm pretty sure it was in the war.
Hmm.
I remember my prof telling me this, and he came up with a solution to Einstein's equations. Any like body of matter is if its radius is two times the gravitational constant times its mass, and if all of its mass is inside that radius, then it will lead to a black hole. It has some type of singularity, and so he was the first to kind of go into that, and then afterwards, Hawking came around, and obviously they did years of research after, but just going to the point of Hawking. So Hawking, yeah, he said about the radiation escapes, and what most theories were working on, they think that the information in the quantum information inside a black hole, it gets it goes to another universe, right? There's some type of wormhole or some type of
A white
universe
hole
on
on the
a
inside.
white hole, yeah, and that's where the singularity is. If you're not familiar with the singularity, it's just like like if you think about a circle, it's just the middle of it, and black hole studying singularities is the most coolest thing to study about because that's where all of physics breaks down. You get crazy infinities in your mathematics and it doesn't make sense. So to understand string theory, you need to understand the information paradox because string theory is one of the ways that kind of accommodates it. It probably accommodates it and it works nice with it in a sense that it for this radiation to leak out and they think that sometimes one theory is that there's quantum information in the radiation still that's leaking out, but how would we be able to describe it? And I think that's where string theory comes into play, is that there's these microscopic degrees of freedom. I don't know how to better explain that, but there's small things leaking out from particles and
I know I know it's not usually wise to trust one's intuitions in the realm of discussing black holes and things, but
hmm
if string theory is true and it predicts additional dimensions of space, would it not be reasonable to think that perhaps the information is just escaping into these other dimensions that we can't perceive yet? Or is that a weird thing to...
I mean, there's no weird thing in all this because you go to a point, and this is very high level physics that I've yet to understand, and
Right.
hopefully one day will. And you go to a point where it's like you don't want to rule out anything, right? All this talk is like it's very interesting because we're getting into deep layers of science, and like to it to be like something that's kind of commonly known what string theory is, because I feel like if you're in the science industry, you definitely know what string theory is, and a lot of people are also against it too. There's a lot of people that don't like string theory and think there's a different way to think about it. But it's just a really cool mathematical concept, and if we could somehow experimentally find a way to test it, that would be great.
We can just get a collider the size of the universe and we should be good.
particle physics is deeply intertwined with astrophysics, and to understand astrophysics, you need to know the standard model and vice versa. And now, I don't know if Tyler, if are you familiar with the work they did at Fermilab a few months back
The
with the muon G,
G minus two
yeah, G,
experiment.
yeah, the G2's experiment. Yeah,
Because I know
Fermi, yeah,
they were confirming results from I think it was a different laboratory over at CERN that
yeah,
came up
yeah.
with similar results of this weird
Phenomenon.
discrepancy in the muon
Mm-hmm.
wobble. I don't know what else to
Wobble,
call
yeah,
it.
and spin, yeah. So, John, I can kind of tell you what this experiment was and how it can lead to new fundamental things of science. So basically, electrons have this intrinsic property called spin, and
Yeah.
it's intrinsic because it's it's that's like you can't like it's there. You can't like you say why it's there.
Yeah,
It's
I
just there.
actually
It's
have
one
a
of those
quick
type of
question already on spin. So I'm familiar with spin. I'm familiar that it's a property electrons
okay.
have. It refers to the
Hmm.
angular momentum. But
Yeah, yeah,
what
yeah.
does it mean to have angular momentum on a point-like object? Because it's not a sphere rotating, which is what the objects I know do when you put angular momentum on them.
Hmm.
How do you even think about that?
Yeah, it's hard to wrap, trust me, it's hard to wrap my mind against it too. I'm still learning how to better describe stuff like that, but it's all mathematical too. Like if mathematically there's angular momentum, but physically there isn't exactly, and
Yeah, that's
like a,
strange to me.
angular momentum, right? But like physically it's hard to see, like or imagine. That's what I meant to say. But if you think about it, there's a wobble or tilt for
Okay,
these electrons, and a muon I think 20 or 200 times
Muon's a
uh
heavy
yeah.
electron, right?
gotcha.
Yeah, it's a heavier electron. It has all the same properties, more or less, and like the way it works. And the muon is another fundamental particle on the
Yeah.
standard model, and it was observed at Fermilab. This is in I think in Illinois. They predicted a certain number with the calculations, and these are all computer calculations done too.
Yeah.
So it's not like someone's just putting in a calculator
That would
and
take a very long time.
yeah, yeah. And they predicted some discrepancy between the spin of the muon, and nothing else describes it in the standard model. Like the weak force, the electromagnetic forces, the strong forces, they don't describe it. And it would be it's very interesting. It's very interesting in science where something isn't what it's supposed to be, because that just brings a whole new area of research and a whole new area of thinking. Obviously, like results have to be confirmed, and there's a whole scientific
Right.
process. But seeing something that's not supposed to be true and seeing someone be wrong, even though we don't want to see someone be
Yeah.
wrong, and like if you're him, you wouldn't want to be wrong. But it's also the best thing in science to be wrong,
Yeah, it's like
because
new
then
physics, you know?
yeah, and it's new physics. So what they think is that it's either like this can lead to some type of fifth force or another dimension, but it's right now it's just something that's in discrepancy, and they have to do more testing and more research about it.
So it's important to note that the standard model of particle physics is one of
Hmm.
our most well-tested theories of physics that we just have.
It might be the most
Yeah,
accurate theory of
Right.
anything.
So
yeah,
seeing discrepancies um, from some of these particles, seeing
hmm,
discrepancies is really weird because it is
yeah.
one of our most well-tested theories that we do have.
It's our bread and butter for like any particle physics related type of
Yeah,
research.
any
Like just in
physicist uses the
physics.
standard
Yeah,
model.
yeah.
Cosmologists, particle physicists, it doesn't matter. Like
Hmm.
we need to make sure these ideas are correct.
And the important thing to notice is like this isn't discrepancy in the fact that it's like if you had like a number like the constant, it's like 0.2 or 0.4. It's not that type of discrepancy. It's like
Right.
in nine and I think decimal places they find discrepancy, and you wouldn't think that's too much in your common day life, but it means the world to these guys. So
Yeah, well,
it's
for this level, for the standard model, it predicts things to such tiny degrees of
Right.
accuracy. It's
Like 10
yeah,
or 11, 12 significant figures. Like,
I think so, something like that. That's
but
where the discrepancy
I
comes
guess
into
what's
play.
cool about this is that typically when people do physics, a lot of times the best they can hope for is to just move that decimal point a little bit farther and get a little bit more accurate. But something like this, it brings in like a whole new sort of
Tries
project.
it different, yeah.
If you haven't, I suggest everyone to watch Interstellar. I think that's one of the best movies to get your
Oh, it's so
mind started
good.
and getting curious about space and learning about it with the amazing acting too. One of my favorite movies. I think it has amazing soundtrack.
Oh,
Right. Sound is
gorgeous.
so
it
good.
yeah, it I think who does the soundtrack is
I want to
Hans
say
Zimmer.
Hans Zimmer, yeah.
Yeah,
It's a
he's
brilliant soundtrack.
if you yeah, if you know who Hans Zimmer is, you know he's the GOAT. Like he's the GOAT in all movies. He did the Dark Knight trilogy, I think he Pirates of the Caribbean, and
Sherlock
he just
Holmes.
Well,
yeah.
I put John Williams on a slightly higher pedestal, but Hans Zimmer is like he's like right there for me. It's very close.
So wait, I'm not too familiar with John Williams. Which
Star
movies?
Wars. I think he actually
Okay,
does
okay.
Indiana Jones. Yeah, some cool stuff.
Yeah, I don't know too much about him, but yeah, I
But
know Hans Zimmer has a special place in my heart because Interstellar and The Dark Knight trilogy are
oh,
like
it's
two of
so
my
good.
favorite movies too, right? So
Super good. And that movie gets a lot of the science pretty
yeah, it
well
does actually.
depicted too.
They worked with there's a cool video to watch on YouTube. It's about 50 minutes, and why I say it's cool is because Matthew McConaughey's he's narrating it, and it's
Hmm.
called The Science Behind Interstellar. It's about a 50-minute video on YouTube, and they kind of go through the science behind it, and it's very easy to understand. Like not easy, but it's not as hard as it would be to actually do the science,
Not
and
much
you kind of
math.
go along with it. Yeah, not too much
Something's
math,
I
and
remember off the top of my head I really liked the black hole pulling the tide, and so the tides were like
yeah,
super high.
yeah.
All the relativity, gravity, moving through dimensions, that sort of thing. That was all super
hmm
cool.
The one thing I also want to talk about is how when I do physics or mathematics, only cl- it's only music without lyrics. Like I can't listen to any rap or hip hop or anything like that.
Right.
Or it's normally soundtracks from movies, Lord of the Rings, Interstellar, uh,
Awesome.
stuff like that.
Yeah.
And I think that's the best way to learn. I mean, with music, if you don't study with music, that's also good too. Like I don't always use music and whatnot, but when I did used to study a lot, I would use like stuff without I guess lyrics, music
Yeah.
without lyrics, and I feel like classical music definitely should. I don't know where it went away in our generation, but it should it's very important to listen to it too because I enjoy sometimes listen to it like even when I'm not studying I'll listen to classical or like soundtracks from movies because they're just like it's something to have in the background where you can still have your focused attention on things you want to do, but you're not listening
Hmm.
to the lyrics and you really like you feel like you're into it more, I guess.
Yeah, yeah. There are a couple of ways you can go about experiencing it. You have that non-intrusive sort of experience, but then you also have the classical music. Classical music is a little tricky. I think it can be good background music, but sort of what you alluded to, it is also the sort of thing that can be good to just kind of focus on and pay attention to and really think about what's going on there. It's really exciting. We
Mm.
talked about that a little bit not long ago.
Yeah,
Uh,
it's something that should be brought up more in our culture today.
so we've talked a lot about the small. Tyler, would you like to introduce us into the very, very big?
You mean cosmology?
Yeah.
Pretty much, cosmology is just like the study of the universe on its largest of scales,
Everything.
basically.
I guess my first question for both of you, and I'm looking at our notes here, and the first thing it says is how general relativity predicts an expanding universe. Now, to me, I didn't know this. Is can you explain the sentence? Are you saying that out of Einstein's equations, they already knew the universe was expanding and accelerating, or just expanding, or what do you mean there?
So how the story goes is Einstein came up with his field equations for general relativity, and he was also a cosmologist or astrophysics, whatever you want to call it. And at the time, we didn't have experimental evidence that the universe was expanding, and so I guess the consensus was that we just lived in a static universe, not expanding. We just static and eternal.
Mm-hmm.
The thing with Einstein's equations, in order for us to have a static universe, we have to add in an extra term that cancels out the like there's like a I don't know how to describe it. It like cancels out the expansion in this term, the cosmological constant, which he claimed was his biggest blunder because later on we did learn that the universe was expanding. Um, However, we still need the cosmological constant not to stop the universe expanding to get us a static universe, but we need it to explain why it's expanding at the rate that it is.
But he had to put it there because he didn't know. He didn't know if it was accelerating, decelerating. And up until 1929, I think, was when Hubble, the guy with the telescope that you've probably heard about, Hubble's
Yep.
telescope, and and
Hubble's
he came
law.
along, Hubble's law, yeah, that's also a big thing in cosmology. And he came along and he noticed that the universe was expanding, galaxies were moving farther apart from each other than they were coming into each other. And then he then was able to, I guess they were able to derive some type of numerical value for this constant that kind of explains or shows the expansion of the universe. They think that it's not just expansion; it's an accelerated
Well,
expansion
at the
too.
time they didn't know that, right? At the time they thought it was
No,
expanding
at the
but slowing
time,
down, right?
Well, we weren't
yeah.
even sure exactly because at that time we only knew of a few other galaxies, and the data showed that they were redshifted, but
hmm
it's hard to. That's all they knew. They couldn't extrapolate further and say that therefore that means the universe is expanding. It could just mean that those galaxies are moving away, right?
Yeah, and red shifting and blue shifting is like when we look at light, right? For those who don't know, and if it's, I think it's if it's moving away from you, it's red shifting. If it's coming towards you, it's blue shifting the light, right? But it's also relevant to dark energy, and I think the cosmological constant gives gateway to looking into dark energy, dark matter. Again, this is a subject that I'm not too familiar about. I know the premise behind it that there is matter that we can't describe with our standard model, and we have no way of describing it.
Okay, so we start with the static universe and we discover
hmm
it's expanding. We go out and investigate why it's expanding and how fast it's expanding. We find out it's actually accelerating, and then it's weird
Yeah.
that it's accelerating. The universe itself is accelerating, but all the universes are staying together because of gravity. So dark energy and dark matter is the principle that kind of explains that.
Yeah, so dark energy explains the acceleration of the universe. I'm pretty sure. Not the like expansion meaning it's expanding and it's accelerating at the same time. So
hmm
it's in both, and I think dark
So,
energy explains the
so
expansion.
I
Actually,
actually I took an astronomy class just last semester, and I emailed
okay,
my
cool.
professor this question. So the universe, according to the Big Bang model that we have,
hmm
would be expanding just from the initial Big Bang, but the cosmological constant is what we think is causing the acceleration of
Yeah.
it's speeding up in its expansion. It's not just simply expanding.
So I guess I also think I'm pretty sure that it's also associated with dark energy, and dark energy is what they think
hmm
that guides this accelerated expansion.
Right.
And
So if I understand it correctly, it's kind of like the energy of the vacuum, because we
yeah,
do know
yeah,
that if you have empty space, just like a region of empty space with no particles or anything in it, there's still like quantum mechanical effects going on, and you kind of have like a foamy sea of like virtual particles coming in and out.
particles, yeah.
And because these virtual particles are kind of popping in and out of existence, it causes sort of like a pressure. So everywhere in the universe where there's a void, there's like a negative pressure that's causing the expansion to speed up. And since the universe is getting bigger and it's just a constant of the vacuum, since there's more vacuum, it's going to be able to exert that pressure more and get bigger. And then because it's bigger, there's more of it. Now it just,
Keep going. Yeah.
yeah.
I'm pretty sure, Tyler, correct me if I'm wrong. Dark matter is like when we use all of our, Einstein's equations and whatnot to figure out and see how, galaxies are formed together. There's a missing matter of that's needed to have that gravity to keep
hmm
everything intertwined with each other. and that's where dark matter is. I think it's like 60-70% of the universe or something like that. It's
Right.
supposed to be dark matter because the
So
gravity
the
doesn't
if we
account for it.
imagine the entire energy content of the universe and we split it
Hmm.
into dark energy, dark matter, and then regular matter, the stuff that makes up you
Hmm.
and I, regular matter would take up about 5% of the total energy content, and then dark matter, which is this gravity that we don't see, makes up about
Yeah,
30% or 25%, and then dark energy actually makes
it's
up
just
about
6%. Yeah.
70%. Yeah. And so dark matter, when we measure the mass of a galaxy, how we do that is we see how fast it's rotating, and we can do calculations using redshift on one side and then blue shift on the other to see how fast it's going. And from that, we can infer the mass of the object. And the problem is the mass if all the gravity is created from just all the normal matter that we can see, galaxies ought to be flying like they shouldn't
Yeah,
be
like
held
this.
together. They should be
It
flying
has
apart
the yeah.
completely. And the only way we can make them not fly apart in the math is to add extra gravity. And we just say that the gravity is spread smooth throughout the galaxy, and it doesn't really clump anywhere, and it's just like an extra source of gravity. I don't know of any
Yeah.
work we've put into trying to understand what this dark matter is, which is essentially just it's gravity hidden inside galaxies that we can't account for.
Well, that's not
Is
very
essentially what it
satisfying.
is. And then
Yeah,
dark
that's that.
energy is just the expansion of the universe, right? It's
Yeah,
what's causing that accelerated expansion.
I don't know why they call it dark though.
Because we can't see
But
it.
They gave a
right,
name like that. If you can't
yeah.
see it, I guess, right? That's why.
Right. Well, it
And
shouldn't be called dark matter. I like the term dark
gravity.
gravity.
Just like wrapping up on all the like the cosmological stuff is that it's so interesting just to like really appreciate what's going on out in the universe and not just on our little blue planet, little blue and green planet. And I like totally recommend, I guess, like when you guys have like if anyone listening or when you guys have a chance, just to, like go stargazing, go to a spot where there's not too much light pollution and really be like see the stars and see what's out there because every time I go and I'm going soon. I'm going in a couple of weeks, going camping into like a dark
Hmm.
sky preserve where there's like not too much light pollution, 2.5 hours away from the
Yeah.
city, and like you really feel at one with the universe. And even if you don't have like if you're not too religious or you're not that spiritual, and like I guess in like nowadays like daily lives, like people are like always in a go 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 mentality, or you got stuff to do, and you don't really take into account for like your existence and like the spirituality behind that and you really find some blissful grateful feeling when you go stargazing too. It's not just looking at something that's cool, it's like you're there, you're feeling it. And yeah, I think cosmology, astrophysics, particle physics, all the stuff we've been talking about is like, even though we're not experts at it, and the fact that we can have conversations like this is great, right? And I think we need more of that in the modern world, and not to be afraid to just talk about it because like I'm learning, I know Tyler's learning, I know John,
Right.
yourself, you're all learning, and it is very rewarding. If especially like if you're doing your first like physics class in first year university or college or at high school and you solve your first question that you don't need help on and like you're like, oh cool, like I know how to do physics and stuff like that.
I
Like
understand something
all
about the
that energy.
universe.
Yep.
Yeah, you learn something, right? And that's the most important thing is to keep learning things and never be like, there's not just one way of learning. It's not just doing math and getting into astrophysics and doing all these courses. Like I said, like YouTube videos, reading books are amazing too. Like I've read a few books which are like really shocked my way of looking at physics and they're written by physicists themselves
Oh
too,
yeah.
right? So
I'd recommend
it's always good
Hawking's
to have.
books and Sean Carroll's books.
Sean Carroll's a really good book. I recommend also Tyson has Astrophysics for People in a Hurry. I read that a few years back. That's a good
It's a
book.
good. Okay.
Another one is Grand Design. I think that's with Hawking and someone else, but I'm not sure. Grand Design, that's the name of it. It's a really amazing book.
Oh yeah. Well, very cool. Thank you for talking with us. Any closing thoughts from either of you?
It was great being on the podcast. I really like what you guys are doing. You guys are amazing people to talk to, amazing people to have a conversation about science. And like I said before, we need to even like people like me. Like I'm no expert. I still don't think I'm an
Yeah.
expert, right?
Exactly.
And we need to have conversations like this just to like facilitate, that curiosity that every single one of us has at the end of the day. It's just that like maybe you have other things going on in your life. You're busy with what, and then like you're busy with a lot of things and you don't have time or like even you don't even think about stuff that's outside of your own playing field, outside your
Yeah.
normal life. But it's good to do that because that gives you some perspective on life and helps you think about the things you do in your regular life lot better, like a lot better as well.
Yeah. Well, thank you very much. I know I learned a lot, and anyone, if you have questions or you want to follow up on some of these topics, feel free to leave comments, and we'll leave links to many of the resources and videos that we mentioned here in the episode. So, thank you.
Thank you for having me.
It's good talking to you.